Hello everyone. In this class we will discuss different types of channels and channel models that we will come across in this course. In different phases of this course we will come across different types of channels. Most importantly, different types of channel models. We will discuss those models and we will also discuss what are the typical physical channels in reality that these models try to model. So, let us first discuss what are the different types of physical channels that through which communication takes place in reality, and then we will discuss their models. So, what are the different types of channels we know of through which communication takes place in today's world? So, the different types of channels that we see one is wired channels. Examples: this is the most common and probably the oldest channels through which we have done communication, and the most common example is telephone line, then fiber optic cables in today's world, third, we have today digital communication also takes place through power communication lines. So, power lines. So, the wires that are used to take electrical power to different sites from the power station. Today we also use those lines to communicate. So, they are used for multiple purpose. The power, the transferring power, electrical power is the primary use of those lines, but at the same time lot of bandwidth is unused in those lines, and that bandwidth can be used to communicate through those lines. Then there is wireless channel. Again, this is very common today. For example, satellite links, mobile cellular communication, uses wireless channel. So, here there is no wire connecting the transmitter and the receiver. The signal goes from the transmitter to the receiver wirelessly through space. And there may be air, there may not be air in the medium through which the signal goes. And there are other channels which most of the times we do not think as channels, but they can be considered as channels through which communication happens. For example, recording channels. So, what are these? When you record something, let us say video or audio on a cassette or CD or magnetic discs, what we are doing is we are recording the signal on the media so that we can play it back in future. And so the signal is going in time from past to future. When we are recording, it is equivalent to transmitting something, and the channel is the recording media and the time, and then when we play it back, it is like we are receiving the signal. So in the meantime, when the signal passes through time, some corruption may take place in the signal. For example, on a CD there may be a scratch. Someone may put a scratch on the CD intentionally or unintentionally, and when we play it back, we may not hear the signal, or we may not get the signal exactly as it was recorded. So this is just like a channel, just like wireless channel or wired channel. It will have different types of different properties than the wire or wireless channels, but nevertheless it is a channel through which communication is taking place. And there are other things which can be considered as channels, though we do not usually consider them as communication at all, but they can be considered as channels. For example, I am writing on this paper, and this is being recorded and transmitted, and you are seeing this image. In the meantime, lot of distortion may take place. When I am writing, I might my handwriting may not be legible. Even if it is legible, maybe that while recording or while editing or while transmission, some corruption of the signal that I wanted to convey takes place. And so this whole thing can be considered as a channel. So this is just like recording channel, except that there may be added components in this channel. I may also do mistake while writing itself. So I have some idea which I want to convey, but while I am writing, I may write erroneously. So I myself can be considered as a channel. So the idea I have in my mind that I want to convey is what needs to be transmitted, but what is received on this paper when I am writing is possibly different from what I wanted to write. So this itself can be considered as a channel. In particular, we can consider a typist typing on a paper, and so let us say we have a typist and the typist wants to type something. So he has some text to be typed, and what he actually types may not be exactly what he wanted to type. So the typed text is what is received on the paper. So the typist may introduce errors in the typed text, and that can be so the typist himself can be considered as a channel through which the text is going through. So this is also a channel. So channels, we know, have also all the typical channels we come across in reality have some amount of randomness. Otherwise, if there is no randomness in the channel, our job as communication engineers will be much simpler. So for example, if we knew that the typist has the error that a particular typist makes are known a priori, we know beforehand what kind of errors, what errors the typist exactly makes. Then the person who is using the typed text, he can actually know which locations or which letters are typed wrongly, and so he can correct, and we can consider that there is the job is quite simple. And even in the telephone line, if we know what kind of distortion the signal is going through, then at the receiver we can possibly invert the distortion, because we know exactly what distortion took place when the signal was coming through the channel, and so we can possibly recover the signal from the received signal. Whereas if the distortion that takes place when the signal goes through the channel, if the distortion has some random part, then we have no way of knowing exactly what distortion took place. We may know the distribution or some statistical properties of the distortion, but if we do not know what exactly the distortion was, we will not be able to recover the signal back fully. So, the difficulty comes because of randomness of the channels, and most of the channels we use can be considered to be of this type. We are transmitting some signal, and the channel distorts the signal in a deterministic way by a function g. Let us call it g. It is a function. This is deterministic, and this may be known at the receiver, may not be known at the receiver, or may be possible to estimate at the receiver. So, there are different situations on that. So, whether g is known, g is unknown, or g can be estimated, maybe with some estimation error. So, whatever it is, transmitted signal goes through some deterministic function, and then a noise is added, and this noise is random. Then we receive the signal. So, it is because of this noise that so much theory for communication engineering is required. If there is no noise, then the only job for the receiver is to invert this function, and if the inverse exists, there is nothing else required. We can invert this function and put it in the receiver, and then we will get exactly what was transmitted. Whereas if there is a random noise, then we will not know exactly what the noise was when the signal was transmitted, and so we cannot really subtract the noise from the received signal. Okay. So this g now, the function g in reality may be too complicated. And this noise itself, the noise also, so we are considering additive noise in this case, even though the noise always may not be additive. This is the simplest model we have, and there is value for simple models for channels instead of considering the most complicated channel, most realistic channel in its all complexity. That has some benefits. So, we will consider additive noise, and we will assume that we know the statistics of the noise. So, for G as well as for noise, we will consider simple models, different models, some are simpler than the others. And why do we consider simple models for channels? So, there are various reasons. One is that it may be too difficult to consider a real channel to start with, because it is too complicated and we do not know how to go about analyzing the system and designing signals, designing techniques for communicating through the channel if we consider too complicated a channel. Whereas, if we start with simple channel, we are able to analyze the channel well and we can develop techniques for communication through that simple channels, then that will also possibly give us some intuition about what kind of techniques will work even for the real channel, which is actually much more complicated than the simple model we are using. So, analyzing simple models can give us intuition about complex real systems, in this case channels. The techniques developed for simple channels may work well for even complex channels, complex real channels, and solving any problem for a simpler channel by itself may be a step towards solving the problem for a more complicated channel. So, we will know what kind of techniques can be used to solve the problem for the complex channel. We will get some idea about it if we solve the problem for the simple model first. So, for all these reasons, it is important to start with simple channel models and see and analyze those channels, analyze how much information can be transmitted through such channels, and also analyze how information can be transmitted through such channels. So, we will now consider different types of channel models. So, the simplest channel model that one can consider is binary symmetric channel. Abbreviated commonly as BSC. The channel model is the following: you transmit either 0 or 1, this is the channel, you transmit either 0 or 1, you also receive 0 or 1. So, whenever you transmit a bit, you receive the same bit with certain probability and you receive the opposite bit with 1 minus that probability. So, if we assume that the probability of error is P, then we can represent this channel model with this famous butterfly diagram. The left hand side represents the transmitted bit, the right hand side represents the received bit. And if we transmit 0, what is the probability that we will receive 0 itself? It is 1 minus the probability of error, because the probability of error is 1 for both the bits. If we transmit 0, the probability of error is P, if we transmit 1, then also the probability of error is P, and that is why the channel is called binary symmetric channel. So, the probability of error is P, so we will have P, we will write P here, we will write P here also, to denote that if we transmit 1, the probability that we will receive 0 is P, if we transmit 0, the probability that we will receive 1 is also P. And if we transmit 0, the probability that we will receive 0 itself is 1 minus p, and if we transmit 1, the probability that we will receive 1 is also 1 minus p. So, this is binary symmetric channel. I would like to emphasize again that this is binary because both the input, that is both the transmitted signal as well as the received signal is binary. You transmit 0 or 1 and you receive 0 or 1. And symmetric, the channel is symmetric because probability of error p is independent of whether you transmit 0 or 1. So, one can consider a next generalization of this channel, that is binary channel, not necessarily symmetric. So, this is binary symmetric channel, and a binary channel in general will be may not be symmetric. So, we will transmit 0 or 1 and we will receive 0 or 1, but 0 will be received with error probability, let us say p. So, this probability, the probability of correct reception of 0 is 1 minus p, and 1 may be received as 0 with probability q and as 1 itself with probability 1 minus q. So, this is the general binary channel. So, this is asymmetric if p is not equal to q. Okay. So, what are the examples of binary channels? Most of the times they are binary symmetric channels. So, examples: an old example may be telegraph channel. So, an old system for telegraph was to transmit English letters using dashes and dots. So, every English letter will be represented by a sequence of dash and dot. For example, E will be represented by a single dot. Similarly, different letters A will be represented by some sequence of dash and dot, just like 1 and 0. So, that is called Morse code. So, this is Morse code, and there will be an instrument through which these dots and dashes will be generated by pressing a switch for a longer or shorter duration. So, the signal, the switch will be connected either for a short duration or a longer duration, and that will convey to the receiver whether this is a dash or dot. So, it is like transmitting 0 and 1. So, dots and dashes are basically can be considered as different names for 0 and 1, and so this communication can be considered binary because it is happening in terms of dots and dashes. In present day, we have local area network, Ethernet cables, and binary signal is always going from one computer to other. So, that also, so Ethernet links, and so these are some common examples. Okay. So, if we have for a binary channel, if the probability of error is small, it is good for us. If it is not small, it is not so good. Is it always true that the probability of error should be small, smaller the better? For example, can we say that if P, consider a binary symmetric channel, consider P equal to 0.001 and there is another channel, so this is binary symmetric channel 1 and binary symmetric channel 2 has P equal to 0.01, then we know that this is better because this has less probability of error. Out of 1000 bits, 1 bit on average 1 bit goes wrong, and here out of 100 bits on average 1 bit goes wrong. Now can you also say that P is the probability of error as high as 0.09, 0.9 is worse than P equal to say 0.3. So out of 10 bits, 3 bits go wrong here for this channel, and for this channel, say this is BSC 3, this is BSC 4. For this channel, out of 10 bits, 9 bits go wrong. So can we say that this is bad? This is worse than this? We cannot say that. In fact, this is better than this channel. Why? Because we can always invert the received bits in this channel. We know that the probability of error is 0.9 for this channel. So what we can do is, at the receiver, we can simply have an inverter which will flip the bit that was received, and then for that channel what will be the probability of error. So we have BSC 3, the channel BSC 3, and then we will implement one inverter. And this whole channel will have probability of error 0.1. minus 0.9. So this channel will be better than this. So this channel itself is more useful than this channel, because by using a simple inverter at the receiver, we are able to convert it to a channel for which the probability of error is only 0.1, whereas the probability of error of this is 0.3, and it cannot be improved by doing some invertible operation at the receiver, like inverting the bit. This is an invertible operation because you can, if you know the inverse of the bit, you know the bit itself. You can invert again and then that will give you this bit, original bit. Okay. So another channel which is common in digital communication is binary erasure channel. So in this channel, the bits are not received erroneously, but bits are received either correctly or they are corrupted, and the receiver detects that the bit is corrupted. So when we say the bit is corrupted, it is like receiving some value which is neither 0 nor 1. We are saying the bit is corrupted. It is so we have received a corrupted bit. So either if we don't know whether 0 was transmitted or 1 was transmitted in that bit time. So we receive, if we transmit 0 or 1, we receive either 0 or 1 respectively, or we receive a corrupted bit which is neither 0 nor 1. So we will call that E, or sometimes X. So E to denote that erasure, so it is erased. So if we transmit 0, there is a probability that the bit will not be received correctly, but it will be corrupted when it goes through the channel, and the receiver will know that the bit is corrupted. So then we will say that the bit is erased. So we have no information about what was transmitted. And similarly, even if we transmit 1, the bit may be erased. So there is some probability. So this erasure probability may be again same for these two or may be different. So we have some probability p, some probability q, and 1 minus p, 1 minus q. So this is called binary erasure channel. This has this comes up in different scenarios. For example, if we are transmitting bits and at the receiver, suppose we are transmitting plus 1 for 1 and minus 1 volt for 0, or plus 5 volt for 1, minus 5 volt for 0, and at the receiver we see whether the voltage level is above 0 or below 0. If the voltage level is above 0, we assume that plus 5 was transmitted. If it is below 0, we assume that minus 5 was transmitted. So it is like, but even if we transmit plus 5, there is a possibility that the received level, voltage level is below 0. So then we will have error. But we can have a system where the receiver sees if the voltage level is near 0. If it is near 0, if the received voltage level is near 0, it says, well, I have received a bit which is very unreliable. Received voltage level is near 0. So that means I am not sure whether plus 5 volt was transmitted or minus 5 volt was transmitted. So I will say that I will not decide on that based on that value, but we will say that the bit was erased. We will assume nothing about that bit. We will say the bit was completely corrupted. Whereas if the value is away from 0, then based on whether it is positive or negative, we will decide on 0 or 1. So then we will have a channel of this type, binary erasure channel. So one is if we decide unreliable received signal as E, if we represent unreliable received signal as erasure, then we will get a channel of this type. Secondly, there are some coding techniques, channel coding techniques, where you first use a code. We will see, we will possibly discuss this in little more detail in some other part of the course. So there are some coding techniques where first a code is used, there is a bit sequence that is generated based on what information that is to be transmitted, and then to save bandwidth, some bits from that bit sequence are dropped, are not actually transmitted. So we transmit after puncturing some bits, it is called puncturing. So we generate a bit sequence based on what message is to be transmitted, and then we puncture that sequence in some fixed locations, and then we transmit that punctured bit sequence. So we are not transmitting all the bits of that sequence. Then when we receive, what we do is we insert those punctured positions. But what can we insert? They are not transmitted, and as a result we have not transmitted any values in those locations. So what is filled in is the symbol E, that is erasure. We assume that what was received was erasure. It is equivalent to receiving a corrupted bit, and then we decode the message from that. So that is when we do puncture, when we puncture a code, then the channel can be equivalently said to be binary erasure channel. and it can be also error and erasure channel. If the transmitted bits themselves are possibly received erroneously, received with error, then there is a possibility that those bits are received wrongly. So then the channel is error and erasure channel. So this is, previously we have considered binary symmetric channel, binary channel in general, and now we are considering binary erasure channel. We can also consider a combination of these two and call it binary error and erasure channel. So what is binary error and erasure channel? It will have it will have 0 and 1, so this 0, 1 and E. There will be some probabilities associated with each of these edges, these transitions. So this may be P1, this may be P2, and this may be 1 minus P1 minus P2, and this may be Q1, Q2 and 1 minus Q1 minus Q2. So this is binary error and erasure channel. So this channel is also relevant in some applications and some techniques. Okay. Now a generalization of all these channels is discrete memoryless channel. What is discrete memoryless channel? Discrete memoryless channel, commonly abbreviated as DMC. We will first discuss what is discrete channel, and then we will discuss why it is called memoryless. A discrete memoryless channel has input alphabet a set. So that is, one of these elements is transmitted, say x1, x2 till xm. So it was like 0 1 for binary symmetric channel, for binary. So this is a generalization. Instead of saying the channel is binary, we are saying we will not transmit only 0 or 1, but we will transmit maybe 0, 1, 2, 3, 4, 5 out of these 6 symbols. So then it is a 6 array channel. Instead of binary channel, it is 6 array channel. So we can have such generalizations of the channels of the binary symmetric channel. So in general, for example, if we have it, if we consider the channel, the typist channel, that the typist is the channel. So he has some idea, he has some text in mind which he wants to type, but he is prone to error. So he makes error while typing. So what is the input to the channel? The input to the channel is the letters of the English alphabet. So there are 26 of them. If we don't consider lowercase, uppercase, numerals, punctuations and all these, we can simply say it is 26 letters, and the received symbol itself is set of 26 letters, maybe including space it is 27. So we have an input alphabet of x1 to xm. Now this x1 to xm will be then A, B, C, D till Z, and then blank space. There are 27 characters. So the input alphabet is m array. There are m possible symbols that could be transmitted. Similarly, the received alphabet is another set of symbols, y1, y2 till yn. Now you may wonder why this set is not same as this, but you should also get the answer immediately from what we have done so far. We have already considered binary eraser channel, and what is binary eraser channel? Here we have input alphabet 0, 1, the output alphabet is 0, E and 1, there are 3 letters. So, the number of output letters may be different from number of input letters. So, we can have in general a different set of received symbols than the transmit alphabet. Okay. And so, a discrete memoryless channel will be specified by input alphabet, received alphabet, and a conditional probability distribution which gives, which is the P probability of Py j given xi. It will denote the probability that y, the received signal, this x is transmitted, y is received. These are random variable x, this is the random variable y. X takes values from this alphabet, y takes values from this alphabet, and Pyj given xj denotes the probability of y equal to yj given x equal to xi. So, these 3 together will specify a discrete memoryless channel, and usually these probabilities, remember there is a transition, these are transition probabilities, transition from xi to yj. Now, these transition probabilities, there are how many transition probabilities? M times n, and usually these transition probabilities are written as a matrix, and this probability is the ijth element of that matrix, and that matrix is called the probability transition matrix. So, the transition matrix is what? It will have P y1 given x1, then P y2 given x1, P y n given x1, and then we will have P y1 given x2, P y2 given x2, P y n given x2. So, this is the probability transition matrix. So, the discrete memoryless channel is specified by the input alphabet, the output alphabet, and the transition matrix, because this gives us the transition probabilities. Okay. Now, why is it called memoryless? It is called memoryless because no channel will be actually used only once. Then what is the use of that channel if you can only transmit once? So, all channels are used for sequential transmission, sequential use, one after another use of the channel to transmit more and more data. So, this channel will be used many times. So, when we transmit one symbol, then we transmit another symbol. What happens to the present symbol when it goes through the channel does not depend on what happened to the previous symbol. So, what was received at the previous symbol interval. So, when you use the channel, we use the channel last time or before, the channel changed the symbols in a certain way, and all those what happened to those symbols does not matter to what is going to happen to the present symbol. and that means the channel does not have any memory, it does not remember its past action. So that is why the channel is called discrete memoryless channel. It is discrete because the input alphabet is a set of finite number of elements, the output alphabet is also a set of finite number of elements. So it is discrete, and it is memoryless because it does not remember its past action. So what happens to the present symbol does not depend on what happened to the previous past symbols. Okay. Now this is the simplest discrete channel, but there can be now different other aspects introduced in the channel which can make the channel more complicated. For example, we can now say that we not only have a discrete memoryless channel. So if we consider the ith use of the channel, we can say that we are transmitting xi and yi is received for xi. Then if we say there is a feedback, so that means what is received is also available to the transmitter while transmitting the next symbol. So when the transmitter is deciding what to transmit at the i+1 symbol, it has already known what was received at the receiver till the last symbol. So it has all the information about what receiver received till the last symbol when it is transmitting the i+1 symbol. So that is feedback. Now with feedback it is a question whether the channel, you can transmit more information if there is a feedback, or it does not matter. Can you transmit more information? That is a very important question in information theory, which was answered by Shannon himself in the negative. So he said, he proved that with feedback you cannot transmit more information than what you can transmit if you do not have feedback. So channel with feedback. Now one can also now say that the channel has memory. Now if the channel has memory, then again that is a generalization. So then can you possibly transmit more information? That is again a question. Now we will consider various other channels . Okay. We will consider different other channels in the next class, but let us now summarize what all channel models we have discussed, and we will also summarize what are the other channel models we are going to discuss in the next class. So in the next class we are going to discuss, first of all, so far we have discussed only discrete channels, that is input alphabet and the output alphabet both were discrete, that is a finite set. Now in the next class we are going to discuss channels for which the input as well as the output is infinite set and it is continuous valued. So we will consider continuous valued channel. In particular we will consider AWGN, additive white Gaussian noise channel, which we will be considering very much in the rest of the course. To continuous valued as well as continuous time, also called waveform channels, because we transmit waveforms through such channels. Again we will consider AWGN, continuous time AWGN channels. Then we will consider linear filter channels, where there is now memory. We will discuss in detail linear filter channel or channel with memory. and then we will consider wireless fading channel. Okay. So, in this class what have we discussed? We have discussed so far different types of physical channels that we come across in digital communication. We come across wire channels, for example telephone line, fiber optic cable, power lines, through which also communication can take place in the extra bandwidth that they have. Then wireless channels, for example satellite links, mobile cellular communication, TV, radio, all these channels are wireless channels. Then recording channels where magnetic media like tape or magnetic discs channels, magnetic discs or CD or even computer hard drive, hard disk, they can be considered as recording channels where you where the transmission is equivalent to when the transmission is basically writing in that media and reception is reading from that media, and in between writing and reading some distortion may take place in the channel. And then we have considered other channels which are little abstract. They are not channels in the physical sense that we usually consider, but they can be considered as channels in their abstraction. So, for example, we have considered a typist who wants to type some text, but he possibly types with some errors, and as a result the typed text may not be exactly same as what he wanted to type, and so we can say that the text has gone through a channel to the typed text. And then we said that all these channels that we have considered have a general type. They are of this type, that you are transmitting something, it goes through a deterministic function and then some random noise is added to the received signal. Now this is deterministic, but this itself in some cases may have some random quantity like wireless channel we will consider in the next class. So G and as well as the noise, additive noise, statistics of the additive noise, they themselves may be very complicated, but we want to start with some simple models. So we start with simple models and develop techniques for communication through such simple channel models. So we have considered binary channel, binary symmetric channel and binary channel in general, and then we have considered binary erasure channel, and in general next we have considered discrete memoryless channel, which is a generalization of all these channels. So in the next class we will discuss some more channel models. Thank you.